now. Boyle's law is related to pressure, so it's better if we do this one first since we just talked about pressure in the previous lesson. So before we begin talking about Boyle's law, we must talk about standard research conditions. You see, the thing is, if we want to be able to compare results and draw conclusions, we need to compare apples with apples. So scientists came up with a set of conditions, parameters under which they would compare gases. And at first they called them STP, standard, temperature, and pressure. And they determined that if a gas is at 101.3 kilopascal, it will have a 22.4 liter volume at 0 degrees Celsius or 273 Kelvin, as long as they have 1 mole of gas. So all gases under these parameters behave the same way. They all have the same pressure, they all have the same volume, if they're at the same temperature, and if we have the same quantity of gas. Now, obviously, it's not easy to work at 0 degrees Celsius, right, in lab conditions. So what they did then is that eventually they said, okay, we have to change these parameters, and let's call a new set of values SATP for standard ambient, which means room, temperature, and pressure. So at room temperature, what are the parameters? Well, the pressure is still 101.3 kilopascal. The volume is now 24.8 liters. Temperature, ambient temperature, is 25 degrees Celsius or 298 Kelvin, and we still work with 1 mole of gas. So this way we can compare results between different gases, different measurements, and see if there's a correlation or not in their behavior. So that being said, we will now move to Boyle's law. Move on to Boyle's law. Now I want to start by showing you a little video to kind of illustrate how Boyle's law works, and then we'll get into the theory of it. So here it goes. So in this video now, you will see the effect of pressure and volume on the size of marshmallows. So pressure and volume of the gas inside this container and the pressure and volume of the air within the marshmallow. So basically what they're doing here, they're removing the gas from inside the glass container, so they're decreasing the pressure, right? Which allows for the volume of air inside the marshmallows to actually increase because there's nothing fighting the marshmallows from taking more space. The air surrounding them has disappeared. It's not applying pressure on them anymore. So the volume, of the gas inside the marshmallows is increasing. And now as they're adding more gas again inside that glass container, it was pressuring on those marshmallows, basically shrinking them back to actually a smaller size than they were before. The relationship between pressure and volume, hold on, let me find my file, here it is. The relationship between pressure and volume, you can see it's inversely proportional. So at constant temperature, so we're not changing the temperature, we're not changing the amount of moles, we're just playing with the volume and the pressure. So if we have constant temperature, constant moles, when the volume decreases, so we have the particles of air are taking less space, the pressure increases. If you think about it, if I'm lowering the size of the container, the particles of air, the gas, will have more collisions together. And we said in the previous lesson that the more collisions there are, the more pressure is exerted on a surface. So by lowering the volume, we're basically allowing for more collisions to occur and therefore increasing the pressure. Now if we look at the reverse, if I'm increasing the volume, the particles will take longer to kind of find each other in the container, so there will be less collisions, and therefore less collisions translates into a lower pressure. So the law is pressure times volume, that relationship stays constant. Okay? So if we're going to compare a before and after or two gases together, we can do it through this equation. So since P times V over here stays constant, we can also say that P1 times V1 should therefore be equal to P2 times V2, which would be equal to P3 times V3, and so on and so forth, because this relationship here is equal to a constant, and since a constant never changes, obviously, well, this side has to be equal to this side, right? Now, if we were to graph this relationship, probably you already know what it looks like because you've done the lab. So let's say we have pressure of 100, volume of 10. So at 10, I have 100 kilopascal. At 5 liters, I have 200 kilopascal. So at 5 liters, I have 200 kilopascal. At 3.3 liters, I have 300 kilopascal. So I'm kind of going backwards here. 3.3 liters, I have 300 kilopascal. And here at 2.5 liters, I have 400 kilopascal. So 2.5 about here. I have this. Aha! We don't have a linear function. I have actually a curve. Okay, so if we see this, that's what my function looks like for P times V. So as volume increases, pressure decreases. If I'm in the lower volumes, pressure should be higher. So I have a curved function, so-called inversely proportional. Now, a little application here. Can you explain the process of breathing based on Boyle's law? Now, I'm going to give you a few seconds to think about it. Actually, what you should do is maybe pause the video, and then when you have an answer, just press play again so you can verify if you were right or wrong. So the answer is, again, we're talking in terms of pressure versus volume, right? So when we're breathing in, okay, we're breathing in. If you take a deep breath, you're going to see that your rib cage is expanding. So that means the volume is increasing. If the volume of your rib cage is increasing, that means it's lowering the pressure inside your lungs. So the pressure outside, the atmospheric pressure, is greater than the pressure inside your lungs. And therefore, it's going to kind of push some air into your lungs. Now, when you breathe out, you're lowering the volume of your rib cage, and therefore, the pressure is increasing inside of your lungs, pushing the air out. I'm sure that's what you answered because you're all a bunch of smarty pants. Next application. We have here the connection to kinetic theory. So I was explaining before that when you lower the volume, you can see here they're pushing down a piece. So the container, it's like a syringe, right? The container can be smaller, it can be bigger. So in this case, if it becomes smaller, you can see that the gas particles are closer together, and therefore there's going to be much more collisions. And the more collisions we have, the more pressure is exerted on the walls of the container. So smaller volume, greater pressure. If you go backwards and you increase the volume, the gas particles will take longer before they bounce around and they hit each other, and therefore there's going to be less collisions and less pressure. So bigger volume, less pressure, smaller volume, greater pressure. Now, how do we apply this mathematically? So let's look at one of the examples in your textbook. So this is it. A sample of helium gas is collected at ambient temperature in a 2.5 liter elastic rubber ball at normal atmospheric pressure. The ball is then immersed in a container of water, also at room temperature, such that the external pressure is exerted on its walls, increases to 110.6 kilopascal. What is the final volume of the ball? So, what are the pieces of info here? I highlighted them or underlined them in color. So, my volume here matches this pressure here. My pressure here matches the volume I'm looking for. So, my initial volume is 2.5. My initial pressure, when they say normal atmospheric pressure, they mean SATP. So, it's 101.3. And then they want to know what volume will the air occupy, or the helium, sorry, at 110.6. So my final pressure is 110.6. What is my final volume? So basically you just plug this in, P1, V1, P2, V2. You solve, you get 2.3 liters. So now I invite you to try these two examples. You have the answers already, but you don't have the solutions. So try them out. If you get these answers, obviously you can stop watching the video. And if not, just pause it maybe and come back to see the solutions if you're not capable of getting these two answers. All right, so here's the solution for the first problem. If you read your problem carefully, let's say you highlight your information. So the pressure on 2.50 liters of anesthetic gas is changed from 101.3 kilopascal to 40. Oops, sorry, not what I wanted. 40.52 kilopascal. What will be the new volume if the temperature remains constant? So I listed my variables here. I invite you to do the same thing when you solve a problem. I know these problems are pretty simple at first. P1, V1, P2, V2 is easy to solve. You'll see all the simple gas laws are like that, but it's a good habit to have because when you get to harder problems, more complicated, you'll have much more variables. It'll make your life simpler if you start listing your info, and you'll have an easier time figuring out how to solve the problem. So like I said, it's a good exercise to do. So I have my variables here. So P1, V1 is what I have in yellow here, and what's in green is P2, V2. So here's the equation I used. I plugged in my numbers. My answer is 6.25 liters. Now don't forget, if you look at sig figs, you have 4 sig figs, 3 significant figures, 4 significant figures. So the smallest amount being 3, my answer will be 6.25 liters. So again, pause the video to do number 2, and then you can play it again to look at the solution if you do not get 120 liters. Here's your solution for number 2. So I have my 4 variables again. So if you're unsure about what goes with what, so a balloon is filled with 30 liters of helium gas at 100 kilopascal. So those two values go together. What is the volume when the balloon rises to an altitude where the pressure is only 25 kilopascal? So you're using P1, V1, P2, V2 again, obviously. You're replacing, and you're going to solve for V2, which will be 120 liters. So it makes sense that if you're lowering the pressure, once again, your volume should increase from what you had earlier on. So there you go. We're done with Boyle's law. So next time you come to class, don't forget to do the exercises on this chapter. Ciao.